Okay, so very important concept, the concept of terminal velocity. So let us understand this concept through the same picture that we have seen before, step by step. So we'll go point by point. I'll open points one after the other, explain it, listen to the explanation carefully. It will make perfect sense to you. So point number one, which comes on the screen, is this. When an object falls, its speed increases with time. This is something you have already understood. So when we talk about terminal velocity here, in this picture, we are talking about an object which is falling down. As it is falling down, what is happening to the speed? It is increasing. Increasing at what rate? At a rate of 9.8 meters per second square. With every passing time, the velocity is increasing with a value of g. Alright? First point, I hope, is sorted and understood. Read it again and again and see if it makes sense. If it does not make sense, maybe you need to go through the previous sections of this same video again. Let me now open the second point. Air resistance acts in opposite direction of the motion. What is air resistance? Let us answer this question. What is air resistance? Have you ever felt air resistance yourself? Yes, you have. So when you are running, do you feel your hair flying backwards and your dresses, they are flying backwards, right? That is because of the air. Air is resisting your movement. It is pushing your hair back. Air resistance, the fundamental principle of air resistance is it always acts in the opposite direction of your motion. So if you are moving this way, that's your motion. You're walking this way. What is the direction of the air resistance? The air resistance is always in the opposite direction. Air resistance, the fundamental thing about air resistance is that air resistance is always in the opposite direction of the direction of motion. This is what this point is saying, and you would have felt it yourself as well. When you're walking, when you're running, when you're jogging, when you're cycling, when you're driving, the air is rushing through your face, through your hair in the backward direction. You can feel it. It is pushing you in the backward direction. Second point, well understood, all sorted. All right, so let's come to the third point. Air resistance increases as the speed of the falling object increases. Let's not consider the falling object for a moment. Let's consider any object which is moving. So when you are moving at a higher speed, air resistance is high. How do you say it? Have you ever experienced it in your day-to-day life? Yes, you have. So when you are walking, you feel your hair is flying back, right? But not so much. But when you are running means higher speed. You're moving at a higher speed. You feel your hair and the dress flying much more. Higher speed, higher is the rush of the air. More is the air resistance. And say that you are riding a cycle, which is even a higher speed. More air resistance you feel on your dress, on your body, and on your hair, right? Next, say that you are sitting in a car. The car is moving on a highway. You take your head out of the window. Don't try doing it in the real life. It can be dangerous. Assume you might would have done it sometime in your life. So try opening the window of the car. Take your head out, or you can also try taking your hand out. You experience a sudden rush of air all throughout in your hair, in your body, on your clothes, right? What does it mean? Higher the speed, higher the rush of the air you feel. Higher is the air resistance. So this is the second property of air resistance. Air resistance increases with the speed. Air resistance increases with the speed. First property that you learned is air resistance acts in the opposite direction of the motion. Air resistance increases with the speed, right? So let us mark a few set of forces here on the ball which is falling. Let us say that the weight of the ball is, I'm writing down some notes here. Let us say that the weight of the ball is W, right? Let us say that the weight of the ball is W. So in which direction does the weight act? Weight always acts downwards, right? So the weight is acting downward. Let us talk about this location of the ball. Weight is acting downward. At this position, say that you are holding the ball, it is not moving. Air resistance will not act. There is no air resistance. Air resistance is always in the direction which is opposite to the movement. So if the ball is moving downwards, which direction is the air resistance? Air resistance is upward. Air resistance is upward, right? So the ball has started falling down. So let us compare two scenarios. Let us compare the scenario here. Let us call this point 1 and let us compare it with the scenario at 2, right? Weight is acting downwards. Weight is acting downwards in both the cases. Weight is acting downwards. Weight will always act down. Remember, these are not two separate balls. It's the same ball, but two different locations of the ball when it is at point 1 and when it is at point 2. Where is the speed higher? Where is the speed of the ball higher? Speed of the ball is higher at point 2 because it has dropped more. This is what this point says. When a ball falls, its speed increases with time. So at point 2, the air resistance is higher. In which direction will the air resistance act? Air resistance will act in the opposite direction of the motion. So let me use a different color pen for air resistance. Air resistance is acting here upward, right? Here as well, the air resistance is acting upward, right? Compare the sizes of the arrows. I am drawing a smaller air resistance here. Why? Because the speed is lesser. Bigger air resistance here. Why? Because the speed is more. More speed, higher air resistance. As the ball is falling down, the air resistance is increasing. Here, smaller air resistance, higher air resistance, right? This is a very important concept to note. Ball is falling down, the air resistance is increasing, and do remember that the green arrow for the air resistance is opposite to the direction of the motion. Motion is downward, air resistance is upward. Air resistance is increasing as you're falling down. How about the weight? Is the weight increasing as you're falling down? Is the weight decreasing as you're falling down? No, your weight will not change, right? The weight of the ball will stay the same because the ball is closer to the earth. You're not so far away in the space that the weight will change. Weight of the ball is same. The weight arrow is the same length here and here is the same length. The length of the arrow of the weight here. Let me use the red color for the weight, sorry. The weight arrow is the same length. This length and this length, they are exactly, precisely the same. Right? Sorry, some mistake here. I'll just erase this. The weight arrow is precisely the same. But the air resistance is increasing. The air resistance is increasing. Let me denote air resistance with the letter AR. Air resistance. Air resistance. Right? Now there comes a point when the weight is balanced by the opposite air resistance. Weight is balanced means they both become equal. Equal. This means, what does balance means? Equal. Let us balance them. So there comes a point. Say that this is the third point when this happens. So what happens at this place? The weight becomes equal to the air resistance. Air resistance. What do you note here? Pay attention. The weight arrow here is precisely the same length as the air resistance. Force, when you study about the force chapter, you'll understand how do you draw force. Force are depicted as the arrow. The length of the arrow represents the magnitude of the force. So here I am drawing both the arrows of the same size. Why? Because now the air resistance has increased so much that it has become equal to the weight. Why has the air resistance increased? Because as this object was falling, it was gaining speed. And we know that air resistance increases as the speed of the falling object is increasing. As the object is falling, the air resistance is increasing in the backward direction. The weight is constant everywhere. Ultimately, at point 3, air resistance and the weight has become equal. So what is the resultant force now on this object? How do you add force vectors, which are precisely opposite in the direction? So if you see weight and air resistance are precisely opposite in the direction, how do you add force vectors? You subtract them. So how much is the resultant force in this particular scenario? How much is the resultant force at location 3? How much is the resultant force? RF is the resultant force. Weight minus air resistance. It becomes 0. Why? Why so? Why? Why is it 0? Because weight is equal to air resistance. At point number 3, the weight has become equal to the air resistance. What next? Is there any force acting on the falling ball at location 3? No force acting. Resultant force is 0. So what happens next? The resultant force is 0. There is a 0 resultant force acting. Now there is a new point on the screen. So what happens? What happens? What happens? Now Newton's first law of motion comes into picture. Now what is the Newton's first law of motion? If an object is at rest and the resultant force on it is 0, it stays at rest. That's Newton's first law of motion. If you have an object, say I'm sitting here, nobody is pushing me, pulling me, I'll keep sitting here. Or if there is certain object lying on your desk, nothing is pushing, pulling it, it will stay there forever. Second scenario of the Newton's first law of motion says, if an object is moving and the resultant force on it becomes 0, the object is not at rest, now it is already moving, and the resultant force becomes 0. What happens? It keeps moving with the same speed forever and ever and ever. Right? So the Newton's first law of motion says if an object is at rest or in motion and the resultant force becomes 0 on it, it will stay in the same state of motion. If the object was at rest earlier, it will stay at rest. If it was moving earlier, the resultant force is 0. It will keep moving forever with the same speed. So this is what happens here. The resultant force on the object has become 0. Now this object, so the object now falls with a constant speed thereafter, and this is known as the terminal velocity. So henceforth, after point number 3, after this particular location, henceforth as it is falling down, as it is moving down, after this location, as the ball moves down and down and down, its velocity will not increase. It will keep moving with the same velocity as it had at location 3. So the velocity it had at location 3, its velocity will not increase henceforth. And this velocity which is reached at point 3 is known as the terminal velocity. Let us take a few imaginary numbers. Say that the velocity here was 0 starting, then it became 5, 10, 50 and 100. Say the velocity became 100. So after this location 3, after this location, these are say meters per second. I'm not writing down the units because of the space crunch here, but you need to understand we are talking about velocity. After this point, the velocity will not increase until this point. If you see, the velocity is increasing 0, 5, 10, 15, 100. After this point, it will keep moving at 100, 100 and 100 and 100 and 100 until it hits the ground. This is what it means. Right? Let us go through the points one by one again. When an object falls, its speed increases with time. So as the object is falling down, the speed is increasing. Air resistance is acting in the opposite direction, and the air resistance is increasing with every passing time. Why? Because the speed is increasing. Now there comes a point, which is point 3, when the weight and the air resistance becomes equal and opposite. They cancel out each other. There is no force acting. Zero resultant force. Newton's first law of motion applies here. No resultant force. The object falls with a constant speed. Right? And also one more thing that you can apply here, if you know the formula that comes from the Newton's second law. Force is equal to ma. Right? Force is equal to ma. What is the force at this point acting on the object? The force acting at point number 3, it's 0. The resultant force has become 0. So let us substitute the value 0 here. 0, force has become 0, mass times acceleration. Can any object exist with a 0 mass? No. There cannot be any object which has 0 mass. So if m times a has to be 0, why is it possible? Only when a is equal to 0. Sorry for the mistake. Only when a is equal to 0. So you can understand it with this other way of understanding as well. Force is equal to ma. So that's another way of understanding things, right? For those of you who have very technical mind, I am explaining using the Newton's second law as well. This equation F is equal to ma comes from the second law. So force is equal to ma when the resultant force becomes 0. Why can the resultant force be 0? When the acceleration is 0. Acceleration, if you see, after point number 3 has become 0. No acceleration. That means the ball is not accelerating anymore. It is moving at a constant speed. So both the Newton's first law and second law can be applied here to explain the reasoning behind the terminal velocity. Right? So after point number 3, there is no acceleration. Acceleration becomes 0. Why? Because the resultant force has become 0. If you want, you can go through this section of the understanding of terminal velocity. Again, you can rewind the video, you can see it again to understand this topic well. Right? Alright, so now we'll take up a past paper question, an examination style question to understand the concept of terminal velocity. So here we have a question. A free fall parachutist jumped from a helium balloon. So a parachutist is jumping from a helium balloon but does not open his parachute for some time. So the figure here shows the speed time graph for his fall. The point B indicates when he opens his parachute. The point B is the point. Point B is the point when the parachute is opened, right? State the value of the gradient of the graph immediately after time t is equal to 0. So you have to determine the gradient. You have to determine the gradient for this portion of the graph. So immediately after the parachutist is falling down. Immediately after the parachutist is falling down. Is there any air resistance? He has just taken a drop. So if say this is your parachutist, he is falling down. He has just taken a jump down. Let us mark the forces acting on the parachutist. Weight is acting down. He has just taken a drop. His velocity is initially 0. He's just started falling from the 0. Air resistance in the opposite direction, 0. Air resistance is 0. Ideally, I should not be drawing any arrow here because no force, no arrow. Air resistance is 0. So what is the total force acting on the object? Total force, it is just the weight, right? What is the formula for the weight? mg, right? Right? So what is the acceleration? Acceleration is g. Force, weight is a force, which is ma. How much is the acceleration? Acceleration is g. Immediately after you take a fall, your acceleration is g, right? So explain why the gradient has this value. Explain why the gradient has this value. Because it's the acceleration of free fall. You have just taken a fall. The only force acting on you is your weight. The only force acting on you is your weight. The formula for weight is mg, right? Another formula for force that we know of is ma. Compare these two entities. So the acceleration on you is g, right? Question number B part. State how this figure shows that the acceleration decreases between time t is equal to 0 and the time a. So why is the acceleration decreasing? How can you say that the acceleration is decreasing between this point and this point? So what kind of a graph is it? It is a speed time graph. And what kind of a curve do you see between these 2 points? What kind of a curve? It's a downward going curve. So therefore, the gradient is going down. So what should be your answer here? Your answer here should be, you have a downward going curve. Downward going curve for which the gradient is decreasing. It's decreasing with every passing time. The gradient is decreasing. The gradient was standing, going down. Let's draw the tangents, right? Let's look at the tangents. The tangent here would be something like this. The tangents are going down, right? The tangent are going down. The gradient is going down. Explain in terms of forces what is happening in the section AB. What is happening in the section AB? Constant speed. What is happening in the section AB? If you see, the speed has become constant. So what do you say? You say speed has become constant. Constant speed. Which means you are not increasing your speed, you are not accelerating. Zero acceleration. Zero acceleration. Zero acceleration means no force. Force is 0. Why? Because force is equal to ma. Acceleration is 0. Force becomes 0. It becomes mass times 0. Mass melt. Just hold on. It becomes mass times 0. 0 resultant force. Between point A and B, what is happening? The air resistance has become equal to the weight. So if this is your parachute is falling, the weight and the air resistance, they're precisely in the opposite direction. The resultant force, which is weight minus air resistance, becomes 0. Why? Because air resistance becomes equal to the weight. Right? Now the D part, a second parachutist of the same size and mass jumped from the balloon with a larger parachute. Larger parachute means larger surface area, so therefore higher air resistance. He also opens his parachute at point B. He also opens the parachute at the same point B. Sketch a possible speed time graph for his fall after he opens his parachute. After he opens the parachute. Larger parachute means there'll be a greater air resistance, so there'll be a more sudden drop in the speed, more sudden. If you see this line that I have drawn here is more steeper, it is more stunning. The earlier line was inclined, this is more sudden drop. And the terminal velocity that you reach ultimately will also be a lower terminal velocity. Earlier this line, let me change the color. So here, this is your terminal velocity. This is your terminal velocity with the parachute not open. TV, terminal velocity with no parachute. Right? You have attained a terminal velocity without a parachute. You open the parachute. You again attain a constant speed after some time, C and D. This is your terminal velocity again with parachute. We are talking about this point with parachute. But if you are using a bigger parachute, you attain a smaller terminal velocity, as in this section. We are talking about this section here. This is the terminal velocity. We are talking about this point now, the last point, with bigger parachute. Right? Rewind the video again to understand if it is not making much sense to you at this point, but I'm sure this is not so difficult to understand. Let me make neater lines here. Right? So this is your terminal velocity, this point on the y-axis, no parachute. TV, terminal velocity, no parachute. CD is the terminal velocity with the parachute, and new line down here, more steeper line. This is the answer for D, terminal velocity with a bigger parachute. Right? I can make some more constructions here to make it more clear. Red color, blue color, green color. Right? Alright, so in the next class, in the next lesson, we'll be taking up more worked examples. We'll be taking up more exam style questions which will include all the previous topics that we have done before. Thank you so much.